We can also have Maxwell's equations expressed in a differential form or point form of Faraday's, Ampere's, and Gauss's law. Sometimes this is quite useful. Now, for deriving this, we use Stokes' theorem as well as divergence theorem. First, let us take the Stokes' theorem, which states that the net flux of the curl of a vector field through an open surface S is equal to the line integral of the vector field around the contour C bounding the open surface. You can look at the illustration defining the Faraday's law on slide 6. Now, you have this open surface of a plastic bag, let's say. Then curl of the vector E. Here, this is the del operator. I hope that you know the definition of del operator and you know how to write this in terms of metrics. Del cross E dot ds equal to the line integral of the electric field along the open path of that plastic bag. So I am using plastic bag as so that you remember the shape. So which implies that del cross E dot ds equal to minus d by dt surface integral of B dot ds. So this comes from Faraday's law. So equating both sides and removing the integral, you can see del cross E equal to minus dB by dt. So this is an alternate or differential form of expression of Faraday's law. Similarly, you can apply Stokes' theorem to Ampere's law. Here you can take the illustration on slide 8. Again, an open plastic bag. H is the line integral along the open edge of the plastic bag, and the surface integral or curl of H is along the surface of the plastic bag coming out. Now, the integral form of the Ampere's law is this part equal to this part, the total current coming out of the surface. Then equating these two parts and removing the surface integral, you can see del cross H equal to J, vector J plus dd by dt. So this is the displacement term, and this is the free current. So you get the point form or differential form of Ampere's law. Now for deriving the Gauss law, whether it is for electric field or magnetic field, we use the divergence theorem of vector fields, which states that the net flux of a vector field out of a closed surface can be obtained as the integral of the divergence of the vector field throughout the volume bounded by the surface. Here for illustration, you can take the closed surface illustrating the Gauss law on slide 9. So it is a completely closed surface with no edges. So total flux coming out of that closed surface, according to divergence theorem, is equal to the volume integral of divergence of the vector field D. So which implies that now this integral of rho dV. So this is coming from the integral form of Gauss law. So surface integral of d dot ds equal to the total charge enclosed, that is Gauss law. So now equating these two and removing the volume integral, you see del dot D equal to rho V. So this is the point form of Gauss law. Rho V is in its units is in coulombs per meter cube. Now similarly, you can find that del dot B equal to 0. Now here is a summary of Maxwell's equation. So here the four Maxwell's equations are given in the integral form. They are nothing but Faraday's law, Ampere's law, Gauss's law for electric field, and Gauss's law for magnetic field. And opposite to that, the differential form of the Maxwell's equations are, or these laws are also given. Now here we have E and D are related. Similarly, H and B are related. Now these relationships are simple linear relationship for so-called linear materials, where B equals mu H. Mu is called the magnetic permeability, mu 0, mu r. Mu r is the relative permeability, and mu 0 is given by this numerical value, and its unit is volt second per ampere meter or Henry per meter. And mu r equal to 1 for non-magnetic materials and more than 1 for ferromagnetic material or magnetic materials. For linear materials, D equals epsilon E, where epsilon is the electric permittivity given as epsilon 0 and epsilon r. Epsilon r is the relative permittivity, which is a unitless number, whereas epsilon is given by this numerical value and has the unit ampere seconds per voltmeter or farads per meter. Relative permittivity is 1 for air or vacuum and more than 1 for other dielectric materials. Let's see what happens when electromagnetic field is going from one medium to another medium. So these mediums 1 and 2 are distinct in terms of its properties. So we distinguish them in terms of its electric permittivity, magnetic permeability, and electric conductivity. So subscript 1 indicate medium 1, subscript 2 indicate medium 2. Similarly, subscript 2 indicate the corresponding field components in medium 2, subscript 1 field components in medium 1. Now these boundary conditions can be defined from Maxwell's equations applying some constraint. We are not going into the details of those derivations. We will just see what are the applicable boundary conditions. Now, regarding the tangential components and the electric field intensity and magnetic field intensity, we can say that the tangential components of the electric field intensity vector E and the magnetic field intensity vector H must be continuous across the boundary between the two media. So here is the tangential component of the electric field, tangential to this boundary. And this is the tangential component of the magnetic field intensity. Remember that both are intensity, field intensities. So they are continuous across the boundary. It means that you have the same value in this boundary. You just go across the boundary, then it is the same value. So this transition at the boundary will not change its value. Well, for E field, it is always the case. Whereas for the H field, this is the case only if there are no free currents, impressed currents on the surface. You can artificially give a current to the surface, then of course it will modify the H field. So in case of surface current, that surface current density is given by the difference in the tangential components. But if there are no surface currents, then they will be zero. That is HT1 equal to HT2. Similarly, the normal components of the electric flux density, D, these are the normal components, and the magnetic flux density, these are the normal components of the magnetic flux density, they must be continuous across the boundary. It means that if you take this point, magnetic flux density here in medium 1 and magnetic flux density in medium 2, they are the same. And here the electric flux density, they are the same. For the magnetic flux density, they are always the same, irrespective of whether you have a current on the surface or not. It doesn't matter. And for the electric flux density, they are the same most often, as long as there are no free charges on the surface. If there are free charges on the surface, then that equation is modified. The difference in the normal component of the electric flux density equal to the surface current density, rho s. And rho s has a unit of coulomb per meter squared. And here the surface current density has the unit amperes per meter. Now, fields at boundary if one medium is a perfect conductor. What is a perfect conductor? They are idealized conductors assumed to have infinite conductivity. So in reality, there are no perfect conductors. Well, you can say that superconductors are approaching the definition of perfect conductors. Otherwise, it is an idealized medium. And the conductivity is given as infinity. Now, there cannot be any fields inside a perfect conductor by definition, and these fields are zero because no fields can penetrate a perfect conductor. That is, assuming medium 2 is a perfect conductor in the previous picture, we get that all the field components with subscript 2 are zero. Then what will happen to fields in medium 1? It will impose some restrictions on what can be the field components in medium 1. Fields in medium 1 are the surface of the conductor, and free or impressed surface currents and free charges on the surface of the conductor, that is the interface between medium and medium 2, they are related by certain relationships. Say, for example, the normal component of the electric flux density in medium 1 on the perfect conductor equal to the surface charge density in coulombs per meter squared, and the tangential component of the electric field intensity on the surface equal to the current density on the perfect conductor. So these are the impressed current densities, where Js, or the current density, is orthogonal to the direction of H. And tangential component of the E field and the normal component of the magnetic field are always zero, whether there is a free charge or free current on the surface. Now look at the constitutive parameters of the medium. We have seen that briefly before, but again it is written out here in a simple isotropic homogeneous medium, or we call it as a simple medium, simple linear medium. Vector D equal to epsilon vector E, where permittivity is value, free space value is given here with subscript epsilon 0. And epsilon r is the relative permittivity. Sometimes it is called dielectric constant, which is a unitless number. Now B equal to mu h. And mu 0 is the free space value of the permeability, Henry's per meter, and mu r is the relative permeability. And we can define the free or conduction current, or the conduction current is equal to conductivity times E, where the vector J is the conduction current. They are not the free or impulse current externally. This current is resulting due to the action of E. So it is not independent of E. You can have a current independent, you can have a current that is imposed upon it, but that is not included in this relationship. And conductivity, sigma, is the conductivity and has the unit Siemens per meter. Siemens is the reciprocal of ohms, and conductivity of one of the most used metal, that is copper, is given as 5.8 into 10 raised to 7 Siemens per meter. Now, some other relationships that are useful are conservation of charge, which state that, which is an expression of the fact that charge can neither be created or destroyed. This is expressed as closed surface integral of j dot ds is equal to rate of change of the charge enclosed in that volume that is enclosed by that surface. So any current leaving a closed surface S implies a decrease of charge within that closed surface of volume V. So charge conservation can be derived from Ampere's and Gauss law. Differential form of charge conservation can be very easily derived from divergence theorem. Del dot J equal to minus rate of change of the volume charge density at that particular point.